Hello everybody, I hope you are doing well. Today I want to present a structural health monitoring method for adhesively bonded joints by the use of a polymer optical fiber. My name is Weiland and I am a research engineer at the Welding and Joining Institute from RWTH Aachen University. In this project we are working together with the Polymer Optical Fiber Application Center from Nuremberg. I want to start my presentation with a little bit an introduction about adhesive bonding and SHM of these adhesive bonds. Adhesive bondings have many advantages. For example, you can bond different materials. It's not high temperature joining technology, but there are also some disadvantages. And one of the biggest thing is that adhesive bonds, we are not able to test them non-destructive to 100%. Therefore, there's always a little bit risk if the adhesive bond is okay or not. And for that challenge, a permanent structural health monitoring system can help, because with that we can detect permanently the stress state of the adhesive bond. That gives us in situ information about the stress condition. The other thing, we can collect long-term data from adhesive bonding, and with those information we can pretty early detect structural changes, damages in the adhesive layer, in the adhesive bond. Therefore, if it's possible to have a good structural health monitoring system for adhesive bond, you can on one side increase the knowledge of the durability of adhesives and increase the convenience in adhesive bonding technology. The testing of these joints, you can divide it in three types. The one big thing which is really standardized is the destructive testing. Then we have, as I told, the non-destructive testing methods, but not for 100% safety. And on the other side, which is on the same level in our opinion, the structural health monitoring, which we can divide it also in two types: extrinsic sensors and intrinsic sensors. So extrinsic means sensor is applied on the adherent. Intrinsic sensor, the sensor is integrated into the adhesive layer. Here you can see a little bit an overview about intrinsic methods for adhesive bonding. Many are pretty known and often used are the lump waves, guided waves, ultrasonic, which we apply the sensors on the adherent, mostly piezo sensors. Then you have resistant-based methods, and the other big thing are the strain-based methods, backphase strain methods. The other methods are our intrinsic methods, where we really integrate the sensor into the adhesive layer, and therefore if the mechanical properties of the sensor and the adhesive layer are really have a big difference, then the influence of the mechanical behavior of the layer is very high, and in most cases it's not a very good influence. Now I want to explain you our method to monitor adhesively bonded joints by the use of the polymer optical. On this slide you see the like an overview what we are planning to do. You see a single lap joint on the left, and into the single lap joint integrated our optical fiber. On the right side you see what happened if we apply force on this single lap joint. If there's no force on it, then you see the fibers in this symmetrical center of the joint, and you can also see the cross-sectional shape of the fiber. It's like a circle, and those light rays are going perfectly through the fiber. And now if we apply force on it, then you see we have the deformation of the adhesive, and this deformation is going through a deformation of the POF. And then we have a change in the cross-sectional shape, ovalization we call it. And then we have some light rays are going out of this fiber. And that's what we are planning to do. We integrate those POF 90 degrees compared to the applying force. The load of the single lap joint is going to the adhesive, is going to the POF. Therefore, we have a change in the cross-sectional shape, and this changed on one side the geometry and on the other side the transmission behavior of the materials. And in that cases, we have a violation of the total reflection conditions, and therefore light rays are going out of the POF, and the output and transmission will go down. And that's what we want to detect. Let's come a little bit more into the materials. POF, what does it mean? Polymer optical fiber. In our case, we use polymer optical fiber from Asahi Kasei, which has a diameter from 500 micrometer. That means the inner core, which is PMMA in that case, has a size of 490 micrometer, and the outer cladding, which is a fluorinated polymer, has a size of 10. And because of the different reflection index of these two materials, from PMMA it's higher than from the cladding. With those fibers you can the light can go through it very well. We integrated those fiber, as I told, in the classical single lap joint. Here down you can see how we did it. We have a 3D printed device where we can integrated the adherents and also this optical fiber, and then we bonded with a 2-component polyurethane adhesive. The one thing is what is pretty important. That's the mechanical properties of the fiber and the mechanical properties of the adhesive. For example, the A modulus of the fiber from PMMA, it's around about 3000 megapascal, and the A modulus of these adhesive, it's about 40 megapascal. If we compare these different to the A modulus of a glass fiber, for example, which is 80 or 90,000 megapascal, then we are possible with that adhesive here to really change the cross-sectional shape of these POF. If we use another adhesive, for example, which is more stiff, like an epoxy, for example, we came in the same range of A modulus of these two materials. So this method, it's really an adhesive depending method and not an adherent depending method. On this slide I want to show you our experimental setup. On the left, that's what I told already. We have the specimen in the testing machine. We have our red LED and the photodiode. We can save the data with a data logger, and we have a power source. In the middle you see our specimen with integrated POF and 2-component polyurethane adhesive. That is one experimental setup. Another setup you can see on the right. There we take a look on the behavior of these bonds with a high resolution camera, and we really want to take a look on the cross-sectional shape of these bonds. So therefore we really cut the adhesive and also the fiber which is coming out on the side from the bond. Here you can see the results of it. On the left, you can see the tensile shear stress over the testing time, and also the answer from the photodiode, the electrical voltage, our sensor signal. First of all, you see what we did was the testing machine. We did a cycle loading 3 times up to 6 megapascal stress of the bond, then down to 0, and then up to 6, down to 0, up to 6, down to 0, 3 times, and after that we tested until failure, which was over 10 megapascal of the adhesive layer. And when you compare these with the red line, which is the electrical voltage, which is our sensor signal, we see we have a very good correlation between red and black. If the stress is going high, that means the deformation is going high, that means the deformation of the POF is very high. The electrical voltage is going down, that means less light will be transmitted through the fiber. And that we can see for all 3 cycles. We have a little bit a shift in the maximum light, which we have definitely to investigate. But up to date we are very proud about these results. And then at the end, when we test until failure, you see really the light transmission is going down, 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 down until the adhesive layer really fails, and then as you can see here, it's not very smooth. It's very, you can see clear that something happened into the adhesive bond. So we are able to really get information about the stress state of the adhesive layer when we only take a look on the red line on the sensor signal. So that was the one thing. The other thing is with our second test setup with the high voltage camera. Here you can see 2 different cycles. The cross-sectional shape. That's at the beginning. You can see it's really a circle, and then, for example, that's by the first cycle at 6 megapascal. You can see that we have an ovalization, and the same is at the third cycle. We have also that ovalization, and that's close to failure. And when we take these shapes here and bring them together, which is actually the picture on the top, you can see we have really a change in the cross-sectional shape of the fiber. And that's the reason why we have the transmission of light here. The other thing I want to show, and that's also the next big thing we have to investigate, is are the adhesion properties of the cladding material, which we have to optimize to have really a good connection between our cladding material and the adhesive bond. Then we guess the change in the shape will be also higher. And what we see in those pictures, we have debonding from the adhesive and the to the cladding material. And exactly in that area where we have these very high stresses on there. And during the cycle, these cracks are growing, and at the end, that's also the reason why the bond fails. So that's the big thing we have to investigate to optimize these behavior. I want to come to my conclusion. I showed you in general an overview about SHM and adhesive bonding. Our method is an intrinsic method, so independent on the adherent but on the adhesive. We saw the direct correlation between the fiber deformation and the stress of the adhesive joint. So therefore we think we are on a good way to develop a new method for structural health monitoring of single lap joints. Two things we have to focus on. It's the big thing is the debonding of the fiber to the adhesive. That's the big thing, and therefore we have also not the maximum load of the joint. That's it from my side. If you have any questions, don't hesitate to ask me. Thank you.